What we are going to draw here is called a ray tracing diagram. And it will give us a very good qualitative idea of what's happening with the rays coming from an object as they strike the mirror. I'm going to start with the mirror we've just been looking at, a concave mirror, under the approximation that we're going to be close to the principal axis. And so I've drawn our concave mirror as a straight line, but to emphasize that it actually has this overall curvature like this, I'm going to put a little tab at the top and the bottom just to indicate that although near the center we're going to treat the mirror like a straight line, a flat surface, it really has this curvature that looks like this. And you should always, whenever you draw a concave mirror, you should draw it like this, straight line with these tabs on the top. And also you should recognize, anytime you see something like this, you should recognize that as a concave mirror. I'm not going to put the cross hatching on the back, but keep in mind the light is all over here, and that's the back of the mirror. We are going to focus on three particular rays that we've already just talked about. We're going to try and see how those rays behave in this situation, always coming from the object, and I've drawn the object over here. We might label this with an O to emphasize that's our object. The light comes from the object, strikes the mirror, and reflects, and we're going to try and figure out where does it go after it reflects. To do this as carefully as possible, to get the most information that we can from our ray tracing diagram, when you do these, you should do them as accurately as possible. And that means use a ruler to make sure you're drawing straight lines as absolutely straight as you can. If you even had some graph paper, you could do it on graph paper, and that would really help you make sure that your lines were all straight. I'm going to be using a meter stick for my drawing, and hopefully it will come out as accurately as possible. I've drawn in our center for the mirror, the focal point, and you should measure these out to make sure that your distance from the mirror to the focal length is exactly 1/2 the distance from the mirror to the center. And I've drawn in an object, and you can put the object anywhere you want. You can make drawings with your objects at all sorts of different places, and the drawing will look different. But in the notes, I think that I put the object exactly twice the radius of the mirror away from the mirror. So if you wanted to do it just like it was in the notes, then you should do that. But you could put it anywhere you want, and the drawing will look somewhat different. So let's assume our object is there, and let's figure out if the reflected rays make some kind of image or not. I'm going to draw all of my rays as coming from the very top of the object. And we'll see where they go. And then we'll come back to that in just a minute. As I said, there are three rays that I will be drawing for this diagram. And I will refer to these as, I'll write them down here. The three principal rays. The first ray is one we were just talking about, a ray that comes in parallel to the principal axis. So I'm going to draw in a ray from my object, from the top of my object, that comes in toward the mirror parallel to the principal axis. So let's do that all together. I'll do this one in blue. So from the top of our object, I'm going to draw in a ray toward the mirror that is parallel to the principal axis. So it's going to look something like this. And we'll draw it all the way in until it hits the mirror. And I'm going to put a little arrowhead on the ray to indicate that it's going in that direction. What does it do? We know that a ray that comes in parallel to the principal axis reflects back through the focal point. So I'm going to draw this ray reflecting back through the focal point. So where it strikes the mirror, it is then going to go down through the focal point like this. There we go. And again, I'll put an arrowhead to indicate that it's going off down that way. let's describe this ray here, our first principal ray. And I'm going to do this in a little shorthand statement notation, just to kind of help us remember where this ray, how it's going in and how does it come out. This ray goes in parallel to the principal axis, so I'm just going to write this as in parallel. Meaning it comes into the mirror parallel to the principal axis, and then where does it go? Out through the focus. So I'm just going to say out through focus. Very good. That's our first principal ray. In parallel, out through the focus. Now, let's draw another one. And for this one, I'm going to draw it in green. Let's remember, if a ray can go from A to B, it can also go from B to A. So if a ray comes in parallel and then out through the focus, a ray that goes in through the focus must come out parallel. So let's draw a ray from our object that goes in through the focus. So the second ray we will draw from our object in through the focal point. So from here, in through the focal point. So this is our second ray. And notice, the more accurately you can draw this, the better your results will be. And again, put a little arrowhead on that to indicate how it's going in. This is our second ray. What is this one? This goes in through the focus. Let's just write that first half down. So the second ray, in through focus. In through the focus. Then where does it go? Well, it's going to reverse the first one. It's going to come out parallel. So from our mirror, we're going to draw it back out parallel to the principal axis. So from the point where it strikes the mirror, we're going to draw a parallel line coming back out. And it's going to look something like that. And again, put a little arrowhead on it to indicate that it's going back out. Then our second ray, in through focus, out parallel. And there's our second principal ray. What's our third one? Our third one is going to use that idea that all of the normal lines always point towards the center. So any ray that comes through the center, from the direction of the center, through the center, will all be reflected right back on themselves, back toward the center, or back through the center. So let's draw that one. Our third ray, and I'll do this one in red, will come in from the object through the center. So from the object through the center, our third ray will look like this. And again, draw in a little arrowhead to indicate the direction. If it comes in through the center, where does it go? It goes back out right on top of itself. So it's going to come in, go right back out on top of itself. And all I have to do is just put another arrowhead indicating back out. There we go. Let's write down our third ray here. Actually, you know what? I'm going to change these, and I'm going to write the first one in blue and the second one in green, and then the third one I'll write in red, just so we can remember those colors. There we go. For the third one, I wrote in through the center, out through the center. Well, let's look at these three rays. In particular, let's look at their reflected rays. We've got our blue reflected ray here, our green reflected ray here, and our red reflected ray here. And what do we notice? They all cross at the same point right there. Hopefully in your drawing they've all crossed at the same point as well. And if we do this as accurately as possible, they really should. That's actually one of the reasons why we draw the mirror as a flat surface. If we drew it as a curved surface, the fact that we actually used a curved surface would throw that off just a little bit. But geometrically, if we use a straight line for our mirror, they actually will come at exactly the same point. What does this mean? All of the light, let me back up for a second. We have drawn 3 rays, but these are not the only rays that are actually coming from the object and striking the mirror. There are an infinite number of rays, essentially an infinite number, big enough for us to think of them as an infinite number. So the rays are actually coming from the object in every direction. And any of those that hit the mirror will be reflected back to the same point. It's only these 3 that we can easily draw geometrically with our ray tracing diagram. But keep in mind, there are actually many, many more. There would be a ray that came up here and then went that way, and then came over here and went that way, and came down here and went that way. So there are many, many rays that strike the mirror and then reflect back to the same point. All of these rays that reflect from the object, remember this is the tip of the object, will come over here together. If I were to take a piece of paper and I could actually get under here and put this here, these rays would actually form a little image of our object on the screen. A little image of that would be formed right on the screen. Very much like if you have a movie projector or something like that. If you go to a movie, there is light coming from the projector that then focuses on the screen and makes an image on the screen. Something you can actually see forming on that screen. In that case, that kind of image is what we call a real image. That is a real image. The kind of image that we saw formed with the flat mirror, that was formed where the rays struck the flat mirror and came away from it, that's called a virtual image. In this case, we could actually put a screen here and the image would be formed on it. I'll come back to the difference between real and virtual images in just a second, but this kind is a real image. What about if that's where the tip of the image is formed? Where's the bottom? Where's the tail of the image? Well, we know the tail of the image. Where does the light from the tail of the object come? Well, we know if this comes straight in here, right along the principal axis, it's going to reflect on the principal axis. So wherever the tail of the image is going to be, it's going to be on the principal axis. So all we need to really do is take our point where the tip of the image is, draw a line straight to the principal axis, and that point on the principal axis, that must be where the tail of the image is. To indicate that this is the tip of the image, we're going to put a little arrowhead on top of that to indicate that that's where the image is formed for our object. The orientation of our object looks like this, pointing this way. Our image then looks like this, pointing that way. We'll come back to that in just a second when we start talking about the characteristics of the image. But I just want to make sure that we are clear about this. Our image then, and we'll draw in our image from the principal axis to the point where all the rays cross. The tip of the image then is at that point. Be very careful when you draw that. Make sure your image goes from the principal axis to the point where all the rays cross, and you put a little arrowhead on that right at that point where the rays are crossing. And then we'll label this, and we can label that with just a little I or something like that. You could write out image or something, but write in something to indicate that's where the image is. If you're in my class and you're going to take an exam or a quiz or something, I'm really very serious about this. I want you to label where that image is. Even though if you draw in the image, it should be obvious. I've had students who draw in the correct image, but then tell me the image is actually located somewhere else. So I want to make sure that you know that's the image, that's where it is. Okay? Very good. Let's take a look at the characteristics of this. First of all, let me ask, is it a real or virtual image? We've already answered that, but let me just write this down. This is a real image. How do we know if an image is real or not? The idea is if you could put a screen at the location of the image, a little picture of that image would be formed on the screen. We will say that if the rays physically cross, it's a real image. So I want us to keep that in mind. A real image, and in this case, what rays are we talking about? For a mirror, it's the reflected rays. So a real image, the reflected rays physically cross. If it is not real, it's a virtual image. For a virtual image, we can just say the opposite. The reflected rays do not physically cross. Some textbooks might describe them in different ways, but I want to make sure for my class, this is what we're going to use. The reflected rays, for a real image, the reflected rays physically cross. For a virtual image, the reflected rays do not physically cross when we're talking about a mirror. Later on, we'll talk about a lens, and we'll have to change this just a little bit. But for a mirror, a real image, the reflected rays physically cross. For a virtual image, the reflected rays do not physically cross. So, do the reflected rays physically cross here? Yes. So, we have a real image. How big is the image? In other words, what's the magnification? The magnification, in this case, from our diagram, oh, that's not what I mean, not proportional to. We'll say approximately. What is the magnification approximately? That is a comparison of the size of the image to the size of the object. Well, in this case, our image looks like it's maybe a third or a half. We maybe will approximate it by, let's say, a half. So we'll say the magnification is about a half. We don't have to worry about significant figures here because it's just an approximation. We're trying to estimate. The half or maybe even a third. We might say a half or a third, something like that. A half or a third. However, let's notice that the orientation of the image is opposite the orientation of the object. The object is pointing upwards, the image is pointing downwards. We say that the image is inverted. When the orientation of the image is opposite that of the object, we say the image is inverted. When it is the same orientation, we say it's upright. So it's either inverted or upright. In this case, our image is inverted, and so we'll say, it's inverted. When an object is inverted, we make the magnification negative. A negative magnification means the image is inverted. If the magnification is positive, that means the image is upright. Very, very good. A ray tracing diagram gives us a very good qualitative idea of what the rays are doing and tells us what the image looks like, approximately. We can also analyze this quantitatively. If we know the radius of the mirror or the focal distance, the distance from the focal point to the mirror, we can actually put some numbers in an equation. I'll get to that in 1 second, but let's define some of these distances. The distance from the center to the mirror, we'll call this the radius of the mirror, which we will label as a capital letter R. The position of the focal point is halfway between the center and the mirror. We'll call that distance, the distance from the focal point to the mirror, we'll call that the focal length. And we'll label that also with the letter F. So F will refer to the point that's the focal point, but we'll also use it to indicate the length, the focal length, which is the distance from the focal point to the mirror. The distance from the object to the mirror, we'll write this as d sub O. This is called the object distance. So d sub O is the distance from the object to the mirror. The distance from the image to the mirror, we'll call that d sub I, the image distance. So d sub I, I'm running out of room here, d sub I is the image distance. Very good. The focal length, the object distance, and the image distance are all related to each other with a very, very simple equation called the mirror equation. I'm going to erase some of this so that we'll have a little more room, and I'll write that down and then we'll stick some numbers in.